So thank you, Sarah. Yeah, I'm continuing on the theme of time integration, and this is work that I have been doing for some years with Colm Clancy. And since he has joined the Maple Club, I thought it was nice to put a maple leaf on the presentation to start. Now, it's a very long talk, but I'm watching the clock. It's at 1, so I'll actually scoot through the first 6 or 7 sections. A lot of this was covered already in the Potsdam meeting, and the presentation is available if details are required later. But I know what happens with Laplace transforms. We've all learned them in undergraduate maths. We've done the exercises, gone to the exam, done the easy question, and then promptly forgotten them all completely. Unless you're an electrical engineer, you've probably never heard of them since. So I will remind you of the basic theory very quickly. You have a function of time. You multiply by a kernel here, integrate from here to eternity, and then you get a function of a new variable s, which is a complex variable. So we will be operating in the complex s plane. Okay, now how do we get back again? Well, there is an inverse transform. It's a little more complicated than the Fourier case, because you now must integrate in the complex s plane. So the contour here, C1, will be, well, I'll show you a picture in a moment. There's a vertical line to the right of all singularities. Okay, and that's it. So if we consider a simple function which is just an oscillation, then the transform is easy to compute, and it's just a function. It's a meromorphic function with a single pole on the imaginary axis. Okay, so we take, for example, a low frequency and a high frequency. We get a pole in each case. A low frequency gives us a pole near the origin. A high frequency gives us a pole farther away. So now we can distinguish in the S-plane between components which are low frequency and high frequency. And that enables us to discriminate. Okay, I think I can skip this. Now you can complete this contour with a semicircle on the left and show that for a large radius that tends to 0. So you now have a closed contour. The advantage of that is that you can apply Cauchy's theorem, and the value of the integral around the closed contour is given by the residues at the poles. So if you have one pole here, that's easy to compute that integral analytically. Okay, so let's see. Now we'll go to 2 components. What's going to happen? It's fairly obvious. You're going to get a transform function which has 2 poles, low frequency pole near the origin, high frequency pole further away. It's a very simple idea. And then we have a picture here. Here's the low frequency, here's the high frequency. And now the big trick is to replace the contour C, this one, by a contour like this, a circular contour. So you shrink that very large semicircle so that it encloses the pole corresponding to a low frequency and excludes the high frequency pole. So this pole is not going to make any contribution to the integral around this. And that's the crafty trick to discriminate low from high frequency. Okay, now how do you do the integration? Well, up till recently we were doing that numerically. So we would replace the circle by some sort of n-gon, a polygon, and calculate numerically. But the essence, or the key point of this talk, is to talk about doing the inversion analytically. And you can do that analytically if you know where the poles are and if you can compute the residues. Skip, skip, skip. Okay, how do we actually apply this? I mean, I'm talking about a function, but now we don't have a function, we don't have the weather, we have the equations. So how do you apply this to a model? Well, let's take a simple equation, which is a kind of a simple atmospheric model. I just take an ODE, which has a linear part representing an oscillation and a nonlinear part. Take the transform now, not of a function, but take the transform of the equation, and here's what you get. W hat is the transform function, and the transform of a derivative drags in the initial value. So your initial value is automatically inducted into the process. And then, if you remember your partial fractions, it's simple to write W hat in this form. Here's the equals from here on. And you see you have a pole at minus I omega, and you have a pole at the origin. So are you going to get a contribution from each? Well, it depends where you put the circle. There's the inversion. If the frequency is small, then it will contribute to an oscillatory component of the solution. But if it's large, it's completely eliminated. So that's the essence of the method. Okay, now I'm going to spare you all the details, but we can write any model in this form. Instead of an ODE, we now have a large vector, state vector x, which is normally has millions of elements. And we have a matrix here representing the linear terms, and we have a nonlinear vector function. But I'm going to scoot right through this section. You don't need to know, as they say, and just say that exactly the same process as I've applied to the ODE applies to the large system of coupled equations. So let me skip. Where did I put the mouse? Okay, if you want the gory details, they're in a couple of papers which appeared last year in the QJ that Cullum and I wrote. So all the technicalities are there. And we applied this procedure to an Eulerian model in part 1 and a Lagrangian model in part 2. And again, the results and the benefits were described before, so I won't spend much time on them, but just briefly, let me jump again. One of the advantages of the Laplace transform scheme over the semi-implicit scheme is that it's more accurate. Okay, the semi-implicit scheme slows down the waves. That's a well-known thing. So here we have a Kelvin wave. The initial data is a pure Kelvin wave, and this is the height at some particular point. So it's a nice sinusoidal variation. The semi-implicit integration gives us this curve here, and of course you can see there's a clear phase error. On the other hand, two versions of the Laplace transform with different cutoff frequencies both represent the phase speed very accurately. So that's clearly a benefit. But we've gone into that before, so I don't propose to spend too much time on that. Let me jump. Okay, it's relatively easy to apply this idea to an Eulerian model, but how do you apply it to a Lagrangian model? Well, let's go right back to the beginning and ask ourselves, what is a Laplace transform? What does it mean? And I'll just show the picture actually. We now redefine a Laplace transform to be an integration along a trajectory. So normally we would fix our point and integrate forward in time. But now I redefine the transform to be the integration along a trajectory. Perfectly reasonable to do that. And that immediately introduces then this idea of the initial value. The initial value now will be the value of the parcel at the departure point. So that will automatically come into the equations. Okay, so let's see how it works. Believe me, I'm being kind to you, skipping all the details. So there's the transform of the equation. And what you see here, then this part comes from the Lagrangian derivative. You get s times the transform of the state vector minus the initial value, but at the departure point. So the Lagrangian advection process is in here. And we then proceed formally, at least as before. We have to decide, of course, what to do with the nonlinear terms. That's a problem no matter what we do. Okay, so I think I can skip the rest of that. Again, the details of all that are in the two papers in QJ last year that I mentioned. Is it any good? Well, we did one test using this scheme in the Lagrangian context. We looked at the problem of orographic resonance. This is a well-documented issue with semi-implicit, semi-Lagrangian long time step models. This shows one such integration using the settled scheme. It's a 24-hour integration. It's a flow over the Rockies, and of course you see spurious oscillations. Now, we did a linear analysis which shows that the Laplace transform scheme should not suffer from this particular nasty effect. And then if I go on, that's the Laplace transform integration. So you can see noise, no noise. So that was another benefit. And again, it's backed up by linear analysis. So finally, I get to the start. So really, this is new stuff from now on. So we asked ourselves, well, you know, what about this numerical inversion is clearly going to introduce some sort of error. Can we avoid it? And the answer is yes, with some difficulty. It turns out to be easy for an Eulerian model, not quite so easy for a Lagrangian one. Okay? And what we end up with is a filtering system very reminiscent of Roger Daly's scheme B. If you remember a very beautiful paper that Roger published in MWR in 1980, where he described 3 different schemes. His scheme B is the one we arrive at. And as I say, in the context of the Eulerian model, it's easy to get there. For the Lagrangian model, the technicalities are more difficult. There's no obstacle in principle, but we have been held up by just overcoming technical issues. So I've written W here instead of X. I can't remember why. I think that's a mistake. But let's start with our usual model equations. We can split them into low frequency and high frequency components. How do you do that? Well, you resolve them into Hopf modes, and there are rotational and gravity modes. So these are the slow modes and the fast modes. Now what Daly did was basically drop this term. He says, okay, let's put the tendency of the fast modes to 0. Now, of course, this is exactly the criterion you use for nonlinear normal mode initialization. So you have a prognostic part for the slow equations and a diagnostic balance equation for the fast ones. And it turns out that if we proceed with the Laplace transform approach, this is essentially what we get, but with one extra benefit, which we'll come to. So we go back to our original equations, and we go through the formalism. Again, I'm not writing the details down. We transform the scheme analytically. That's to say, we transform the equations analytically. We diagonalize the system, so this matrix has to be diagonalized. And then we invert analytically. Now we can do that. If we know where the poles are, we can do that. L star is just my notation for the integral around the circle. It's a modified inverse Laplace transform. Okay, and here's what we get. It's written in a cumbersome way, but if we were to assume the nonlinear terms are constant, then this is actually the analytical solution. So we have an exact solution for the slow components, which is very nice. You can't do much better than exact. And for the fast components, we have the usual balanced fast waves, which is nice. And this compares very closely to Daly's scheme B. But the advantages are, of course, for the Laplace transform scheme, we actually have the analytical solutions, whereas with Daly's approach, he would use something like a leapfrog method to advance the slow components. Okay, how are we doing for time? Perfect. So there's a reasonable question here that a reasonable person might pose. Is that if we're going to transform, and then we're going to transform back again, what in goodness name are you doing? Why don't you just stay in the time domain? Well, of course, it's a matter of insight, it's a matter of understanding, and a matter of guidance. The approach shows you what you're doing and the consequences of your actions. You can't, if we were geniuses, we could just write down the answer in the first place. But it's not that easy. So that you can think of the Laplace transform approach as a way, a means of getting a scheme which has advantages. But in the end, in the numerics, you don't have to do any Laplace transforms because you've got your scheme. I mean, it's a direct analogy. I just thought about, say, a digital filter here. You have some sort of time sequence, X, and you want to do something with it like extract some frequency band. You do this by applying a digital filter. This is just a classical finite impulse response filter, and you get your outputs. And that's all done in the time domain. But of course, the essence of how it works is encapsulated in the coefficients. And in order to choose them, you really need to go over to the Fourier domain. and look what's happening to the frequencies. So the Fourier framework is a way of designing the filter. But once you've got it designed, you're in the time domain. So it's the same here. We end up with a time scheme, but the Laplace transform approach is the way of getting there. So let's see what it looks like for an actual model. This is the STSWM model. I've finally known how to pronounce that. Spectral transform shallow water model, which is an NCAR model, shallow water model. And then this is the absolute vorticity, divergence, and geopotential. And these are spectral coefficients. And the hat means I'm in the Laplace transform domain. So I have the transform of each coefficient for all three variables. Now, previously what we would have done is invert these numerically using a polygon. But if you look closely, you find we can see where the poles are. There's obviously a pole at the origin. I didn't write out R and Q explicitly, but we have expressions. I just took D, and D has this expression here, and clearly it has poles at plus and minus I omega L, where these are the gravity wave frequencies. So we know where everything is, and we know the values. We can do the inversion analytically. And we do that by inspection, if you like. We can apply the modified inverse by inspection and get the solution. Okay, so what about the Lagrangian model? Now I spare you again. I don't write down the details because they're quite intricate, although in principle straightforward. But it can be done, and the details, hopefully we'll get a paper out of this eventually, and the details will go in there, or maybe even into an appendix, which nobody will read, but they'll be there. Okay, so I better show you. I'll finish with some results. So, first of all, the Eulerian model. In all cases, I'll take a time step of 10 minutes, fix the spectral resolution, no explicit diffusion, the L infinity norm, and as a reference, a higher resolution semi-implicit model. Okay, and I'll show you two plots for each case. In the first plot, we're using the older numerical inversion of the Laplace transform with two cutoff times, 3 hour and a 1 hour. And then on the second plot, the corresponding results using the analytical inversion. So here's three curves. This is the reference semi-implicit, and these, the blue and the red, are the resulting errors for the Laplace transform scheme. And this is bad because there's a sensitivity to the cutoff period, which there should not be for this case. So this is an unwelcome distinction between these. So when we look at the analytical results, here they are, and you see there's effectively no sensitivity to cutoff, which is what we would like. That's good news. That's bad news. That's good news. Okay, if we do test case 6, which is the Rossby-Horowitz wave, we're going to show the same configuration of plots. Again, the numerical and the analytical, and it's much the same story. There's a sensitivity to cutoff here, but with the analytical inversion, the results are the same for the two cutoffs. Good news again. Okay, so in the analytical case, this isn't an issue. The integrations match closely. Now, I have only very preliminary results for the Lagrangian case, but I'll show what I have. Here, in all cases, we'll take a cutoff period. I'll just fix the cutoff at 1 hour. This is detail, detail, detail. And again, the reference will be a semi-implicit higher resolution run. So again, I'll show two plots, but in both cases, we'll have a numerical and an analytical solution in each case, in each graph. We fix the cutoff period and have the same reference. But in the first plot, the time step is 10 minutes. In the second plot, half an hour. So let's see what happens. And here's the numerical and the analytical integration with a short time step. So that means we possibly have the code correct. It's running. It looks reasonable. It doesn't prove anything, but that's the result you want. If we go to half an hour, you see there is a difference between them. The analytical inversion is actually somewhat more accurate, not dramatically so, but it's certainly in the right direction, more accurate than the numerical. That's good news. Well, good news is nice, but I have to give you some bad news now. That's that we haven't finished yet. Okay, the results for the Rosby-Horowitz case are quite bad, but in order to get things running quickly, we did something not so good. If we take this term, similar term in the vorticity equation would be F delta. We took these terms. We need the transform of these, but of course, along a trajectory in a Lagrangian model, the Coriolis parameter is varying along the trajectory. We cheated and just took it outside as a constant and just transformed the vorticity or divergence. So clearly that's not a good thing to do. It was just something we did in a hurry, and we know that it's not good, so we're basically, that's work in progress. We're looking into that to formulate that term in a more precise way, but the way forward is fairly clear. So we're optimistic. So they're the results that could have been written down a year or so ago. There's nothing new. We have a scheme that filters the high frequency waves effectively. It's more accurate, and that's shown both analytically and numerically, and we get rid of orographic resonance. But what's new is the analytical inversion gives us a more accurate scheme than the numerical, and it removes this spurious sensitivity to the cutoff, which is good. With the Lagrangian scheme, I just say wait and see. Hopefully we'll see you at the next meeting with more complete report. Thanks for that. I'll leave it at that.
Peter, I certainly recognise your description of learning about Laplace transforms years ago and not having seen them since. So,
I have a question. Peter, you have mentioned for the Lagrangian formulation, you are using a Laplace transformation. I could see that for the time variable, since it varies from 0 to infinity, I could relate that. I'm not sure for a Lagrangian trajectory, it's a space variable. It will vary from, it could be, in principle, it could be from minus infinity to plus infinity. So you are getting into a different kind of an integral.
Oh yes, it's quite it's a different. As I said before, you sort of go right back to the beginning and you ask yourself, what am I doing with this transform? And you can choose. You're free to choose which space you use at each time. It's perfectly open to your choice. So logically, with the Lagrangian derivative in the frame, you choose the trajectory. You could choose any path in space.
Peter, can you comment on the computational expense of the Laplace transform scheme compared to the semi-implicit scheme?
Yeah, it's actually going not to be an issue at all now. There is an overhead with the numerical inversion, and that's one of the reasons we wanted to get away from it. Because with the numerical inversion, you have to take, let's say, an octagon. You have to do whatever you have to do 8 times. Right, there may be symmetries to reduce that, but effectively, you've a severe overhead. So we were motivated to look at doing the inversion analytically. And I mean, I can say hand on heart, we don't believe there's any reason to be concerned about computation expense. It's quite comparable to a semi-implicit.
Sean?
How about globality and locality? Your scheme is global with the half mode and so on. So essentially, how would that float on tomorrow's computer?
Oh, I have no idea. I mean, it's the same. It's not a new issue. I mean, it's the issue to do with spectral models. You know, the time scheme is not really the issue here.
But would that have an application eventually on grid point models?
I hope so, but when we haven't looked at this, yeah. But I mean, that's a problem for the future, for sure.
Yeah, if you wanted to take this into 3D, I imagine you'd be looking at working in vertical modes. And the issue certainly with deep models is the vertical structure of the internal mode starts getting very questionable as whether it's really got a lot to do with the real solution. And this is a particular artifact that they depend on where the upper boundary is. And so do you think this method has any future in 3D models where you really have to use that sort of expansion, I suspect?
Yeah, I think it has. I mean, I mean, the external mode is very dominant.
Yeah, that's okay, but it's the internal mode.
Yeah, but I'd say the first few internal modes should be okay. Should be
Well,
resolved.
no, there is an issue with those because of the fact that the amplitude of the linear solution expands enormously with height, and which is completely not what the actual data does. So when you project the data in the model onto these modes, you get some very funny projections. So I'd be quite worried about using a mode which depends on those projections being realistic.
Yeah, again, isn't this a problem with semi-implicit approach anyway? It's not.
Well, no, you never go into modes. You just solve a semi. You never have to do a normal mode expansion in semi-implicit methods. So I'm just wondering if this is going to get in the way of using this type of method.
Well, you do. I mean, you resolve. Surely, you do a transform with a vertical structure in the semi-implicit model.
No, you don't. No, you don't.
You don't?
No.
Okay, we need to have a coffee.
Okay, thanks.
Thank you.